Hi class, today we're going to talk about how we get the exact age of a fossil or a rock layer. Instead of just figuring out the general order of things that one is older than the other, we're going to find out how we know things like, hey, the dinosaurs became extinct 66 million years ago. How do we know that it's exactly 66 million years ago? And that's what we're going to figure out. The process that we use is called absolute time. Now, absolute time basically allows us to determine the chronometric or the calendar age of a rock or a fossil, okay? And we use a process called radioactive decay, which is the breakdown of unstable atomic nuclei releasing radiation. You can think of it this way. You know, you have a friend who's kind of an oddball, and they're a little unstable, and they're usually heading for a breakdown. And radioactive decay is like that too. We have atoms that are unstable, and they're going to break down from one thing into another. These are called radioisotopes. And they have an unstable nucleus, and it's going to decay over time, just kind of like your weird friend. So how does this work out a little more specifically? Essentially, we have our unstable parent isotope. In these examples, you've got two different ones. You have uranium, which is your unstable isotope, and it decays into thorium-234, and it gives off a helium particle. We also have another unstable isotope, parent isotope called carbon-14, which will decay, give off an electron, and become nitrogen. So we're going from a parent to a daughter isotope, one that is unstable and one that is stable. And what we do then is we compare the ratio of the unstable atom, the amount of them, to the amount of stable daughter isotopes. And we know the rate at which they decay. And so if we measure this amount and that amount, then we can figure out how long it's been around. To give you an example of that, it would be like if you really, really liked Starburst, okay? And you went in your room with a package of 100 Starburst and you ate half of the package every hour. Then your friend could come in and they could count up the wrappers that are left on the bed and the floor, and they could figure out how long you've been there, because we know that Starburst are the unstable parent isotope and the wrappers are the stable daughter isotope. And we can just compare that ratio and figure out how long you've been there. If there's 50 wrappers, you've been there an hour. If there's only 25 Starbursts left and 75 wrappers, then you've been there for 2 hours, etc. So it's just kind of a simple way that we can go about determining the age of something. And we can verify that by going back just a short period of time to things that we know the age of, and using carbon-14 or something, and then comparing that to what we know. And that's how we know it's a legitimate way to measure the age of something. Okay, so how do we do this? Let's give you an example here. Okay, so the term that we use to measure age in this is what's called half-life, okay? And half-life is basically the amount of time it takes half of the unstable atoms, the parent isotope, to turn into the daughter isotope. So again, you can think of the Starburst example. In that example, it took 1 hour for half of the Starburst to become wrappers, okay? So here we go. We're going to do this. You're going to fill out this graph in your notes. We start with a mineral sample right here that has 100% of the parent isotope. And then after one half-life, which we know is how long it takes for half of that to decay, now we have 50% parent and 50% daughter isotopes. Again, we go another half-life, and we go from 25% parent to 75% daughter. So the daughter ones are the black dots, the parents are the white dots. You can start to make estimates now. If we go another half-life, what it's going to be. It's going to be half of 25, right? So 12.5% is parent and 87.5% is daughter. We go one more here. We're going to get 6.5% parent and 93.75% daughter. You can do it again. It's roughly going to be 3% parent and 97% daughter. And eventually we're going to get down here to tinier and tinier amounts where it's going to get really almost impossible to read the ratio of parent to daughter because the fraction is going to be so tiny. All right. So what are some isotopes that we use for radioactive decay? The most common one that you'll hear about is carbon-14. We already talked about this. Carbon-14 has a half-life of almost 6,000 years. And so eventually it will run out. It has a limit in the 30,000 year range roughly. And so what are some items that we can use carbon-14 to tell the age of? Native American tools would be a good one, mammoth bones, Roman pottery, those sort of things would be used. We would use carbon-14 for. Please make sure you're filling out your table on the bottom of your note sheet with this information. Our next up here is potassium-40, which decays to argon-40. It takes 1.3 billion years. That's a really long half-life. So we can age date things that are 100,000 years old to things that are 4.6 billion years old. It's good for something like dinosaur bones, which are at least 66 million years old. So that allows us to determine those age. We can't use carbon-14 for dinosaur bones because they're too old. There's no carbon-14 to measure anymore. Another example is uranium-238. It decays into lead-206, and it takes 4.5 billion years for the half-life. So really old stuff, like the oldest rocks on the moon and the oldest rocks on the Earth, we would use the decay of uranium-238 to tell the age of. All right, you're going to do an assignment today, a little lab activity simulating radioactive decay. Please follow the directions and submit that to the Google Classroom when you're done.